but
Okay, got it.
Hi,
Can
everyone.
I ask a quick question to Dan?
Yes, let's start.
This is a scientific question, and
Okay.
so we talk about the dark matter and dark energy, and I learned that there is a 70% of the dark matter and 23%, 20%, 30% of the dark energy. No, the other way around.
Yeah.
Energy 70%, matter 23%. Physics is matter and energy, right? Physics is nothing but matter and energy. So interconversion we have seen. Now we are saying the dark energy because we can't see it. This means that all the radiations, all the electromagnetic radiation so far they are unable to detect that. Now we have two choices. One is that the lowest photon energy, highest photon energy is the gamma radiation, lowest photon energy is the radio, right? Radio wave. So now my question now comes is that we must have to push to go beyond the gamma energy and photon energy, radio photons, to see the other radiations, because this is just a limitation that our matter can generate, and when matter can generate these radiations, another matter can detect them. That's what we do. Okay, that's why where that in research is going on. Is anybody doing in the field that they can explore other radiations, other beyond this electromagnetic spectrum that we know?
Yeah, so the dark energy. Sorry, I'm suffering from a terrible cold, so I'll be hacking and sneezing and coughing the whole time. And I'm high on all sorts of cold medicine, so I may not be as cogent as usual. But the dark energy is not electromagnetic. It's not photons outside of the range, super gamma ray or super radio. It has very different properties. It kind of the key characteristic of dark energy is that so as the universe expands, the density of matter drops, right? That makes sense. And radiation drops even faster because it's also getting redshifted. But dark energy, its density is always the same. You can double the amount of volume in the universe, and dark energy is still the same density. It started out at a low level, but matter and radiation have dropped below it. So it has this weird property where it's almost like it's always bothered me. It's almost like it violates conservation laws. There's more and more of it all the time because there's more and more space. It appears to be a property of the vacuum. And there are different forms of dark energy, but the cosmological constant is simply that energy associated with the vacuum.
Yeah, can I add one remark there, because you enlightened me somehow? Okay, you said that there is a property of the vacuum, and so the Einstein went from Newton, saying that the fastest energy that we can detect is the light speed. Okay, so he limited everything there. Then he has to change the space and time. Okay, then when everything relativity come. Now you are saying the vacuum is the property there. So this must go. It must go beyond the. We have to expand the searching the radiation, because what you are saying that we see the dark matter because we see the different radiation. So no, the thing is that it's like if we shine the light to a matter, it flourishes. We see the fluorescence, okay, and then we may not see the light that excites that object. Okay, it's something like that. So the dark matter is emitting the radiation that our detectors, our telescopes can see, but dark matter itself can be detected only if we have a higher energy than gamma. And then it is going to the vacuum, means that vacuum is not vacuum. Vacuum is, there is energy. We are in the sea of the energy. So we all are in the sea of the energy. Everywhere is the electromagnetic radiation of all kinds. Okay, we are in the sea. That's why I think, this is my opinion, but you may ask, I mean, you may talk with your level, you are in the higher level of contact. So you may ask this question to them. And it seems to me that the vacuum is not vacuum, but then the Einstein's law is no more acting there. So that has to go. Vacuum is a material.
Vacuum is something.
So like one, I give you one example. The neutron density is so high that if we have this much of neutron, we cannot lift it. That is so high. So at the moment we can lift it because it is so teeny, so teeny. That's why everywhere is neutron. So this means that dark matter probably we have already in our here. Okay, but the thing is that how to detect it. Detection means that not the radiation, electromagnetic radiation converting from one form to another form, like let's say we sign the object by gamma radiation. It emits the visible radiation, and we see that visible radiation. So that is just what we are seeing here. But yeah, thank you.
So the dark matter, the dark energy and dark matter are totally different things. Dark energy is probably a property of the vacuum or something related to it. There's not much more we can say about. We're totally clueless on the dark energy. The dark matter is probably more pedestrian than dark energy. It comes in two forms, machos and WIMPs. Those are the acronyms. Machos, massive compact halo objects like black holes and white dwarfs that may be too faint. But that can't account for all of it. Perhaps 20% in the Milky Way and less on cosmological scales. So most people think that the dark matter is WIMPs, weakly interacting massive particles. These would be exotic particles created in the high energy conditions after the Big Bang. And since they're weakly interacting, they interact via gravity and the weak force. But now there is some evidence. So you'd have WIMPs and you'd have anti-WIMPs, and since they're weakly interacting, they normally don't annihilate, except in high density regions. And it has been noted that there is more gamma rays coming from like the center of our galaxy than we can account for with normal processes. So there's possibility, that's not proof, that this is WIMP, anti-WIMP annihilation, but we can't seem, in my knowledge base may be a little out of date here, but a few years ago, this was the big story. We, perhaps that extra gamma ray signature from the center is WIMP, anti-WIMP annihilation.
Quick remark here, because somebody will be listening this video and they may have a thought about it. That's why I'm putting a small remark and then I will stop. So every matter has wave nature, right? Every matter has wave nature. So like the electron has wave nature, light has wave nature, photon sometimes behaves like little particles, behaves like wave, electron, and so on. So this means that every matter has a wave related, and wave means the energy related. Okay, I did an experiment during my master's degree in Germany, where there is a molecular beam interference. So this means that we excite the molecule, potassium molecule in a pure transition by a laser light, and then these two rays from 1 point to 3 meters at the end of the molecular beam detector are detected, and we see a very clear interference pattern. So this means that the molecules behave like a wave there. Yes. And this means that our body has an equivalent of wavelength. Okay, we cannot detect that because we do not have a capability of doing that. Okay, so that's why these waves are there existing, but we are not able to detect. So that's why you said that there is a very weak but high energy interaction is there, and that seems as a vacuum here. So this means that we must find a way beyond the gamma ray. We must find. That's why I'm surprised why it is not there, because this gamma ray and radio waves are the just what we see, and this to me looks obvious, searching the radiation beyond the gamma and that one. Okay, thank you very much. I appreciate it.
Yep. And by the way, I hate the universe works this way. The wave particle duality bothers me to my core. It should bother all of us to our cores. It makes no sense, but it's the universe that we apparently live in. Anyway, great introductory discussion. Brett, I saw your hand.
Yeah, I just like to say that if the dark matter doesn't have a direct wave interacting with photons, then it doesn't matter how high energy or low energy the photons are. If there is a, matter antimatter annihilation that makes photons, there's that. But it all depends on how it interacts. It doesn't mean that if you go to a higher and higher photon energy, then all of a sudden it starts interacting. I mean, it could be that the matter just doesn't interact electromagnetically directly.
That's true. If it's all one or the other, matter, antimatter, and it's weakly interacting, we'll never see it electromagnetically. The only hope is that if it is WIMPs, there's, the WIMPs and anti-WIMPs were created in kind of equal numbers, and we'll have annihilations in dense regions.
Right. Do you have you followed the Mond people's stuff recently? They've gotten a lot of press recently.
I haven't followed it recently, but in general, my understanding of Mond is it just doesn't. It can explain this or that, but not all.
Yeah.
I think the typical example is the bullet cluster.
Yeah.
I'm trying to remember here. Giant cluster of galaxies, they merge. And the stars, the galaxies are pressureless, so they move clear through, but the gas is pressuresome, and so it separates. And let's see, if Mond were correct, it would, I forget, but it follows one or the other, and you don't get that signature. So, but yeah, I haven't followed it closely, carefully. I don't put a lot. I never bet more than $1, but if I had to bet $1, I'd bet it against Mond. But anyway, yeah, it's always great to start with fun stuff like that. Let's move on to more pedestrian things. Does anyone have any questions, comments about where they are in the material, either teaching it or learning it? Anything that needs to be addressed? Okay. Let me share my screen. And I am recording good. Okay. Slide you over here, spread you out. Okay. So let's see. Seeing the doctor this afternoon. So anyway. Okay, so we've gotten through lab 1 finally. We took a week longer than we normally do, though there were a few orientation items that I never got to. And of the ones that are remaining, most of them I'll just fold into the sessions as we encounter them. But I just want to make sure you're aware of these resources before moving into lab 2. So, and these were included. Let me see here. Here's our list of videos, and on the orientation video down here, I included a bunch of links. I think I pointed these out before. In these links, you can find this stuff or stuff like this. But as you're orienting your students, if you're trying to get them excited about things, here are just some generic images that you can use. I'm going to put this in the chat. I don't think I've shared this yet in our sessions. Pictures of, like, here's a picture of Chololo, and if you see it on a larger scale, our little telescopes are down here somewhere. Some videos, I think these videos are linked in lab 1, where you can see the construction and the dome's opening, and And just some other pictures of the telescopes, mostly in Chile, but also in Australia. Oh, this is a fun one. This is from our webcam. You know, there's a drop off here. And so here you see prompt telescopes and some other telescopes as well. And here you see the cloud tops just right beneath us. And so these are kind of fun images to get students excited. We, of course, have a radio telescope, 6 stories tall, 150 tons, and 20 meters across. The largest optical telescopes, 10 meters across. And again, you can get them excited about that, and there'll be more of these in the near future. And also this image that we mentioned before, you may want to use it during orientation to help with that expectations issue, where they're expecting Hubble quality images and they'll be getting this in the case of Mars at best. And so setting those expectations right from the onset can be a good thing. So there's some resources for you there. Also, to get them excited, I'm going to show you something lower on this page, but I have a little video here at the top that's kind of fun. This is an occultation of Jupiter by the moon back in 2013. These are images taken with the same telescopes that they use. I think this was the Prompt 5 telescope. And you see Jupiter there, and then here comes the moon. And yeah, I see smiles. It always makes me smile the first time I see it. And of course,
I feel like there should be like some ominous, Jaws music or
Yes,
something
exactly.
as this moves in.
Dun, 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 dun. And then we play it again where we change the brightness and contrast. That should pop in any second now. There we go. So you can see the moons a little bit more strongly. And you'll notice the variation on the moon just because that's atmospheric turbulence. I mean, you can see it here too, but you can really see it here on the moon as it covers up.
Atmospheric turbulence in the Earth.
Say again, please.
Observation turbulence in the Earth, not in the moon, right? So
it's the Earth's atmosphere.
Yep. Sorry, I didn't get it. Yeah, it's definitely the Earth's atmosphere. But anyway, the reason I want to take you to this page is we have 2 astrophotography groups that have worked with our telescopes over the years. One's still active. This first group's not active, but these are all the APODs they got. And you can click on any of them to go to their page and get more information. And here's the other group that they actually built a 32-inch, the Prompt 7 telescope, and they've gotten a lot of APODs. So we're over 24 APODs at this point. And this, you got to be a little careful. You don't want to ruin expectations. You don't want them thinking they're going to take pictures like this. Each of these is like 40 hours, 50, 60 hours of observing time put together. But maybe it gets them excited that they're using the same telescopes that people are using to do stuff like this, and the same telescopes professionals are using to do cutting edge research. And I'll just stick that link in the chat as well. And as we mentioned last time, we've added to Lab 1 this opportunity for them to make a simple red, green, blue image. And so maybe this gets them motivated there a little bit as well. Okay, so where are we? We've done orientation stuff. We did Lab 1, Week 1, Lab 1, Week 2. In Week 1, they learned how to use Skynet and place their observations. In Week 2, they learned how to use Afterglow. Okay. And so now we're on to Lab 2, and Lab 2 is one of our manual labs. We have 2 versions of it, the version that everyone does and the version that I prefer. Very few people do the version I prefer. And this is the Earth and the Seasons lab. So this is designed to, the standard misconception about why it's hotter in summer and colder in winter. That is emphasized in elementary school, middle school, high school, undergrad. For some reason, we've latched on to this as the thing students must know. And I have a little bit of a gripe against that, because there are many things in astronomy that are not well understood. Almost everything in astronomy is not well understood by the general public. But for some reason, we've hooked on seasons, and probably because the sun and the moon are the or the sun in particular, brightest thing in the sky. Introductory astronomy is organized from brightest to faintest, or closest to farthest, or historically. And so this topic is first in standard curricula. And so I think that's why it's been latched onto as the thing that everyone must know. But anyway, that little gripe aside, most people think it's a very important lesson. And so we have a lab built around it. And this is one of our labs that is not a Skynet-based lab. As we talked about, sorry. As we talked about, we sat down at the beginning of this and said, what are the major lessons that are typically taught in introductory astronomy, and designed activities around them instead of saying, okay, these are the tools we have, what can we do with them? And two things fell into the category of misconceptions that we should probably address. One is the seasons, the Earth and the seasons. And the other is the nature of the Big Bang. So lab 2 and lab 8 do not use Skynet, but are designed to address these misconceptions. So lab 2 would be, you've probably done a lab like this at some point in the past. Okay, so it doesn't use Skynet, but it actually works well in the sequence, particularly if you use the Globe version. The Globe version is a little slower, it takes 2 weeks, but it also takes 2 weeks to collect your Skynet data for lab 3. The point is, the data collection for lab 3 is a little bit lengthy, so let's throw in a non-Skynet lab before it. Now, we have 2 versions. So I'm going to present the Stellarium version to you today because that's the one that most people use. But let me just kind of pitch the Globe version for a moment first. This is an example of the Globe setup. Actually, we have a slightly improved version here where we changed the lights to something a little bit more ideal. But I like this version better for pedagogical reasons. It gives the students kind of the God's eye perspective. They're out above the Earth, separate from the Earth and the sun, looking down upon the solar system. And I think that helps them visualize the geometry a lot better. The Stellarium version is ground-based, so the worm's eye view instead of the bird's eye view. And so there are some benefits to that. When we figured out how the seasons work, historically, we figured it out from standing on the ground and looking up, and Stellarium replicates that. So there's some advantage there. But in terms of really understanding what's going on, I think the Globe version is better in extracting yourself and looking down upon the system. But to do this requires a little bit extra. First of all, you have to have the space to build these kinds of setups, these kinds of lab kits. You have to have the money. These kits are not super expensive, but once you add everything up, it's about $80 per kit. The basic idea is you have a globe. Globes are a standard 12-inch globe. You can get them pretty inexpensively. You put a light on the globe. We went through different iterations of this. We started with a 12-inch ring light that gave nice uniform illumination. But back when we started this, you couldn't get them very bright. They were mercury lights, mercury filled. So there's some safety issues because they would break easily, and they didn't give you a strong illumination. So then we tried regular lights. If you use a single light, you get kind of a spotlight pattern. And what you're really trying to do is get a nice, even terminator, a straight up and down line here from the base of the globe straight up, separating day and night. And what we do in this lab, whether it's the Globe lab or the Stellarium lab, is we're measuring things like length of day. Well, we're measuring 2 things. Length of day, we're doing it for a whole bunch of latitudes and all the 4 seasons. And we're measuring the sun's angle above the horizon. So length of day gives you duration of illumination. Of course, the longer a spot is illuminated, the warmer it gets. And the angle of the sun, which we use midday as the reference, gives you directness of illumination. That's, of course, also a big factor. I know you know these things, but maybe as you'd explain it to a student. So those are the 2 things we're going to measure. And it's a very manual lab, particularly with the Globe lights manual, but even with Stellarium, what we're doing is we're going through and we're measuring these 2 things for a whole bunch of latitudes and a whole bunch of seasons. So it's really to develop their intuition through repetition, good repetition. They're going to do enough of these measurements that they just kind of know how it will work. Because there's clearly a problem in teaching this concept. We keep doing it, elementary school, middle school, high school, undergrad, and then they still forget it. You've all seen the Harvard video. We talked about it on the first day. The Harvard graduates still didn't know it. So they forget it. So hopefully doing it in a lab setting may help there. So repetition, developing intuition through repetition. And so if you're measuring length of day, for example, since we won't be talking about the globe, I'll just mention a few things, how we do it with the globe. You put your location, like this is Northern Hemisphere winter, the Earth is tipped away, and they pick a city that you put it on the terminator. You follow the line of constant longitude, changing latitude up to the hour circle, and the hour circle at the top of the globe gives you a time. Then you move that object facing the sun and do the same time measurement. That's half the length of day, double it, you have length of day. Or if you want to measure the angle of the sun at midday, you put a protractor flush on the globe with a little string tied to the 0, 0 spot, hold the string out horizontally, and that angle that you measure on the protractor is the height of the sun at midday. So that's how we do it in the globe lab. Now, so, a single light gave a spotlight pattern. We tried 2 lights, which gives, it's not quite perfect, kind of wavy, but now they make 12-inch ring lights in LED that are very bright. So we've switched back to the ring lights. And if you have the space to do this and you have the funds to do this, I encourage you to think about switching to this as you can. If you're only making one setup, you just need the globe and the ring light. But if you have many students in the room, and we do 2 students per setup, you could do 3, but I think once you do 4, you have someone just standing around not doing anything. So if you have many of them in the room, you also have to build these PVC cages and get some black felt and drape it around the cage. We even drape one in front of the cage, leaving just the spot with the globe open. Of course, to change the season, you change the orientation of the globe with respect to the light. But anyway, that's the gist of the globe lab. I'll walk through all these same measurements in Stellarium for you in just a moment. Okay. If you want to do this, email me. I'll dig out my parts list with links to things on Amazon. A few might be outdated, but you'll get the idea, and you can take care of that.
Quick question.
Yes.
Did you say that change in season is one is the Earth's orientation with respect to its orbital motion, and another is the Big Bang?
Yeah.
What is that about the Big Bang?
So the Big Bang, so that would be Lab 8, and we'll talk about Lab 8. But the big misconception is everyone thinks that before time began, space was there, empty, and all the matter was concentrated here, and then boom, and it filled the vacuum. And that's not at all what the Big Bang theory is. That's easy to disprove that misconception. So it's actually an inexpensive lab. We use rubber bands and things, and we can actually build Hubble's law from the rubber band. They have godlike powers and can stop time and make measurements and then continue the expansion. So we'll come to that in Lab 8. For here in Lab 2, to change the seasons, yes, the globe moves around the light, but then you have to kind of change. Suppose we move the globe to the other side of the light, and the northern hemisphere is pointed towards the sun, and so that corresponds to coming back to this place and rotating the globe such that the axis is pointing towards the sun. Instead of rotating the whole apparatus, the box, and as I move the globe around, you'd have to shift the box and the lights and everything. We just spin the globe. And that's a conceptual thing that can actually cause confusion. So anyway, that's the globe lab. So think about it. When I create your WebAssign sections, I give you both 2S and 2G, and you then turn off whichever one you don't want to use. Okay, let's go to the lab. Here's 2G, here's 2S. I'll open up a 2S because that's what most of you will be using. And I have one already open. So I think it will open over top of it. Yeah, there we go. Okay. Standard stuff at the top. We have our overview videos, introduction, background, and procedure. And they're also, as I've said before, listed on the Intro Astro YouTube site. Here we are into Lab 2 Stellarium version. If you view the playlist here, you have like a 2-minute introduction to the lab. And again, in these videos, I speak slowly for the accessibility work that we may add to them. We already have enhanced accessibility versions of these videos, and the fact that I speak slowly makes it easier for people who have to read lips. And we may add sign language in time. So if you're watching them, you can just play it at like YouTube lets you play at faster speeds. You don't have to listen to me drone on. And then one for the background and one for the procedure. And often students may watch the background video instead of reading the background sections, or they may just skip the background sections. This was an attempt to at least get them to focus on the background a little bit instead of skipping to the procedure. And then we also have the how-to videos that are embedded in the lab. Okay. And this is going to be standard at the top of every one. Then we have our important instructions. We have a link to the observing guide, which is telling them it's time to put in observations for a future lab. Come back to that in a second. And then the other notes we have, note there are questions in the background section. Some of the labs have points in the background section. So if the student's going to skip over the background section, they're going to lose points in this case. And so this is just a little heads up that there are a few questions for them to answer there. Also, just a reminder to review the sources of error from the previous lab. If the students don't do that, they'll keep getting the sources of error wrong throughout the entire lab sequence. In fact, you in your pre-lab talk may want to take a moment and talk about the correct answer to the sources of error questions in the previous lab. And then we have our usual warnings and pieces of advice that stay the same always. Now, let's pull up the observing guide, which I think I have it open here. After you do your pre-lab talk, before they get to work, you're going to say, okay, we're going to put in our observations. And so next up is Lab 3. You may actually want to put them in during the second week of Lab 2. If you're doing the Stellarium version, you can do Lab 2 in a week. If you're doing the Globe version, it takes 2 weeks. So what we do at Chapel Hill is they put in their Lab 1 observations on the first week of Lab 1. And the first week of Lab 2, they're going to put in their color observation. Sorry, the second week of Lab 1, they put in the color image observation, because we're going to do that with our students this time. Instead of it being optional, we're going to have everyone do it. First week of Lab 2, they put in their observations for Lab 3. And then the second week of Lab 2, there's a lot of extra time, so we're going to do our color picture in the extra time. Anyway, whether it's the second week of Lab 1 or the first week of Lab 2, you want to put in those Lab 3 observations. It says here you want to put them in 3 weeks before the due date. And then there's some notes. If I slide down to Lab 3, it tells you what procedure in Lab 3 you want to look at, a link to the video tutorial. Some extra things. This is a repeating observation. Lab 3, we're going to watch a moon go around a gas giant. So they have to not just observe the gas giant again, but set it up to repeat. We're going to observe once a day for 14 days. There's a note here to use all prompt telescopes, though that's the general advice right now. Since Cerro is still locked out, I recommend that you select all telescopes. I'm going to put in a Lab 3 observation for you in just a second so you see how it's done. Even though it's asking for 14 observations, you don't need all 14. We just need to see the moon in various places of the orbit. As long as 5 or 6 come back, they're going to be okay. So they don't need to freak out if they don't get all 14. And of course, the more you have, the easier it will be to see the pattern. There's also a note here that if they didn't get a Venus observation in Lab 1, they may want to try again. Okay, so let's put in the Lab 3 observation, then we'll come back and do the Stellarium part of Lab 2. Lab 3 observation. Get optical observing. Again, you do this with all the students at the same time to guarantee they get their observations in, so they have no excuse. I'm going to add a new observation. We're really lucky this time of year. Let's take a look at the sky here. There's the sun. And as soon as the sun sets, Mars is a little bit low in the sky, maybe hard to observe, but we got a lot of stuff in the night sky here. We got Pluto, Saturn, Neptune, Jupiter, Uranus. All the gas giants are out. More towards the end of the night. Anyway, let's put in Jupiter. And the students will pick. They don't do all four. So this is for lab 3, where they're going to monitor a moon going around a gas giant, and they're going to determine the orbit. And it's a Kepler's 3 lab. But they got to get the observations in soon. And have them pick a gas giant. It has to be one that's currently observable. Right now, all 4 are. There are pluses and minuses to each. Jupiter is the prettiest. It's the most fun to observe. Being the closest, its moons are spread out, makes it easy to identify. But sometimes Ganymede, which is the moon that we're tracking, is so far off, it's off the chip. For the smaller format cameras, they may lose Ganymede for an observation or 2. Not a big deal, but something to be aware of. Saturn is also quite pretty. Being farther away, the moons are closer in on the image. And so they'll be using Titan in that one, and it's always there. So Saturn's pretty ideal. Uranus is the toughest. So your students who want a challenge, they can do Uranus. Being farther away, the moons are closer in. They're kind of in the sky glow quite often. They may have to change the brightness and contrast to pull out the moons. There are no really bright moons. They're all medium brightness moons. So it's a little bit more challenging. And then Neptune, that's the easiest because there's only one moon observable. It's so far away, the moon is right next to it in the image. And so they don't need to use Stellarium to do moon ID. So that's for your lazy students. But they can all pick one. And students love it when they have choice. So the fact that they get to pick their planet gets them more excited. Anyway, I'll put in Jupiter here. Remember our default setting, -12, 20.5. The moon phase, which is not written in the lab yet, 130 are good defaults. For like Jupiter and Saturn, you can go all the way down to 0 if you wanted to. It could be right next to the moon. You can still see everything. But 130 are good defaults. We don't need the advanced settings. You check the air mass chart. And indeed, Jupiter is observable second half of the night in many, many different observatories. Make sure you have some observatories above the gray line. And choose the filter. The lab's currently written that the observation's in V band. Save and continue. And then here they'd select the prompt telescopes, but since we have our problem at Cerro Tololo, we're recommending that they select all telescopes. Again, you can do that just by clicking on the orange button. I'll pick, I'm not sure which one of these to pick. This is the longest list. They only have one time account, and it will select everything they have access to. That's probably the way you want to go until we get Tololo back. Save and continue. Again, it's the generic system, and the lab tells you what. So we want 1.03 second exposure in V band. And we got the pink stuff working again. It was broken. But this means this observation, which is 3 seconds, 300ths of a second on our generic telescope, will go through on any of these. You see how the exposure times are being scaled. They may saturate the planet. That's okay. We're interested in the moons. Prompt 6 is more efficient, so that scales down to 0.02, and that's faster than the shutter, so it's pinked out. If you want, you can tweak it a little bit. There, now prompt 6 is an option, but it's a Tololo, so it's not really an option right now. Anyway, the big difference is down here under the advanced options. We're going to want to repeat this observation 14 times with at least 1 day in between. It's pretty much the only thing that's different than before. We want to make sure this is checked. Continue on next available telescope if interrupted. That's the default. It should be checked. If they only pick one telescope, well, if they don't click this and they start on one telescope and then that telescope goes down or is weathered out, they're going to wait. If it goes down for 2 weeks, they'll get no data. But if it's clicked, continue on next available telescope. If a telescope's not available, it'll just go to the next one that's available on the list. So they'll get their data back from a variety of telescopes, but at least they'll get their data back. Then you save and continue and submit. I don't need this data, so I'm not going to submit it. That's the lab 3 observation, and I'm just telling you now because you want to put it in early. Questions about that? Okay. Now, since we're using telescopes that are not just prompts, some of them are not as good as others. And so just be prepared for that. But here, you don't need a pretty picture. You just need to see the moons. The planet could be saturated, doesn't matter. So it should be okay. All right. Back to lab 2. I've gone on, I've taken my time, so I need to speed up a little bit. Okay. Lab 2, goals. As I said before, length of day and how it changes with latitude and season. Height of the sun in the sky at midday, how it changes with latitude and season. They're also going to measure Earth's diameter. You can do it the same way as you measure the height of the sun in the sky at midday at 2 locations separated. It's the ancient Greek experiment. We want to get the Earth's diameter because that's the base of the cosmic distance ladder, which is the theme of the course. So by the time we get to lab 4, we're doing Earth baseline parallax that becomes stellar parallax and then standard candles and Hubble's. So to do Earth baseline parallax, we need Earth's diameter. So this sets the base of the cosmic distance ladder. Equipment for the Stellarium version is just computer with internet. If you're in the globe version of this, there's a parts list. 2 background sections. One on just kind of defining longitude and latitude. And I have this hiccup in my brain. I can't, when someone says line of longitude, I don't know if they mean line of changing longitude or constant longitude. So, and some students run into this. So I spell it out explicitly throughout the lab. Longitude or lines of changing longitude run from -180 west to 180 east. Changing latitude runs from 90 to +90, pole to pole. Here are lines of constant longitude and constant latitude as well. The first exercise is just to use Stellarium. Let's see, let me bring up Stellarium. To measure the longitude and latitude of a location. We're going to be picking lots of locations. You're going to need to know how to find their longitude and latitude. Again, F11, because it opens in full screen mode. If you don't know F11, it's a nightmare trying to figure out how to minimize it. You go to location, you type in, for this one, we do Chapel Hill because it's Skynet headquarters. You find it in the list. It sets the latitude and longitude here. We tell them to round it off to the nearest degree and use negative signs for south and west. Okay. In the globe version, they also calculate a % error, and we have this great opportunity to discuss precision versus accuracy as part of the sources of error that you can't do in Stellarium because it's 100% accurate. But imagine doing this on the globe. There are only lines every 15 degrees, so they have to interpolate between those lines. That is a source of imprecision. Half the class will be wrong in the high direction, half in the low direction. That's imprecision. Chapel Hill is not on the globe. Closest city is Raleigh. Raleigh is east of us. So everyone will be off in one direction. That is inaccuracy. And so I know you know these things, but it's a great, if you're doing the globe version, it's a great lesson that you can also convey as part of the sources of error. Anyway, they're just practicing how to measure the longitude and latitude of a site. Now in the second section here, this is on the nature of the seasons and the big misconceptions. Start with some terminology, defining solstice, defining equinox, and then the big question, why is it hotter in summer, colder in winter? And I normally ask the students, and someone will raise their hand and they'll answer it correctly because maybe they've already seen it in lecture or they read the lab, and the ones who raise their hands are usually the smart students, and they're showing off that they know the correct answer. So don't stop there. Say, okay, that's right. Though a lot of people get this wrong. What's the other answer that is sometimes given? And then people will say proximity. Some people think it's hotter in summer because the sun is closer. And so then you can dispel that. Here's a 2-scale image of Earth's orbit. Of course, the sun and the Earth are not to scale, but the orbit's to scale. It's almost perfectly circular. We're about the same distance away always. In fact, it is, of course, a little bit elliptical, which means we're sometimes closer. We're closer to the sun in Northern Hemisphere winter. So that dispels the idea of proximity. Also, if it was a proximity effect, the whole Earth would be warmer, not just the Northern Hemisphere, but also the Southern Hemisphere. And most of them know that when it's winter in the north, it's summer in the south and vice versa. So you can go through that. And so then you go back to the right answer. It's the tilt. And Earth is tipped 23.5 degrees, probably when the moon was formed. The collision tipped us over, and then tidal forces held it in place. It's why all the globes are tipped 23.5 degrees. So sometimes one hemisphere will be tilted towards the sun, and you get longer illumination and more direct illumination. And sometimes it's hemisphere is tipped away. It changes as you orbit. And then there's a simple question here: why, when it's summer in the north, what's it in the south? But then we set up the rest of the lab here. We're going to be looking at length of day as a function of latitude and season. We're going to be looking at the sun's horizon angle, how far it's above the horizon at midday, as a function of those two things. Okay, so now into the procedure. Start with length of day. And first we do a practice measurement using Chapel Hill, and then they're going to do a bunch of measurements. So the practice measurement. So let me just show you. I'll go into Stellarium. So first they go here, and there's a note to check that we're in the local time zone. In the previous lab, we used UTC. But here, the measurements make more sense if you stay in the local time zone of wherever you're measuring. That way, the sunrise times, the sunset times are all kind of make good sense. And we tell them to enable daylight savings time, though it doesn't really matter. They're measuring lengths of day. It's subtracting two things. So even if they're in the wrong time zone, it would work. But anyway, we tell them to use local time, use the daylight savings time, so they get values that are familiar. And we tell them we're going to do Chapel Hill summer solstice. So first, let's find the sun. Use the search window, go to the sun, I'll put it in the center, and zoom out a little bit. And then we want summer solstice, so that's June 21st. Sometimes it's the 20th, sometimes the 22nd, but that doesn't matter that much. Then they're going to decrease the time until it crosses the horizon. And let me make this big. That can be a little challenging to see, particularly when it gets close to the horizon. It all blurs out. And you're like, yeah, wait, what time does that happen? So first of all, zoom in. And what I do is I put my finger on the screen with my fingernail right on the middle of the sun. You can't see this, but that's what I'm doing. And I lower it until it's at the horizon, not the tops of the trees, but at what appears to be the horizon. Now in Stellarium, you have options. You can go and you can change to ocean mode. That gives you a nice clean horizon. But I actually prefer that they use the default setting. It's some farmland in France is what they use for the default setting. Because if you were to send them to go outside, the actual outside, and do this, there would be obstructions. And so this is a great source of error. And so they mark that time, and then we're going to do the sunset time, moving forward. And here we have a lot of obstructions. So there's the sun, got my fingernail on it, and I'm going to run forward in time. Maybe I'll zoom out a little bit. You don't want the tops of the mountains, but kind of the base. So again, lots of obstruction, sources of error, but the auto grading is very generous. Okay, and so they get a time there, and they put these in here. Sunrise time, sunset time. They have to convert to decimal hours, and In labs 1 and 2, and we'll do this in the rest of the labs as I update them, we've added these links to example calculations. Sometimes students get tripped up converting hours, minutes to decimal hours. So here's an example of how to do that. We're hoping this will help a lot. Every computation, we're going to give an example now. So decimal hours, sunrise, sunset, subtract them as length of day. We tell them the true, actually we don't use that terminology anymore. Professionally best determined value is 14.54. They calculate a percent error. Again, it came up over here this time. We have an example of how to calculate percent error with the absolute value times 100, etc. To help them along, and discuss significant sources of error. For the Stellarium, for the Globe Lab, there are many, but for Stellarium, trying to identify the sun's center, given the sun's glow, difficulty identifying the horizon, given obstructions. They may also say that solstice sometimes doesn't land on the 21st, or that the sunrise and sunset did not occur on the exact moment of solstice. It doesn't really matter for solstice. Solstice means standstill. The sun is, on the exact same position on the horizon for many days in a row. It stands still before it keeps moving on the horizon. So I don't give points for that, but you can if you want. Okay, so they practice with the 1. I'm just zipping through, but if you have questions, interrupt. And then they pick 5 cities. And we've updated the lab to hopefully make this easier. 1 a few degrees south of the Arctic Circle. Make sure they're south. 1 in the middle of the Northern Hemisphere, 1 near the equator, 1 in the middle of the Southern Hemisphere, and 1 just a little bit above, north of the Antarctic Circle. And we've actually marked the ranges on the map here to help them. Now, the one they're going to have problems with is the one that's just a little bit above the Antarctic Circle. Again, they love picking their own cities. They'll have a hoot with that. But there are very few cities down there, so we tell them to do Biscoe Island, but they have to add it. So this is how you add it. Biscoe Island's down here somewhere. And, they click down there, and then they can update the longitude and latitude to what's in the lab. And we have them type in Biscoe Island and set the country. They can use mean solar time. They add it to the list, and then whenever they type in Biscoe Island, they have Biscoe Island. It's just a few degrees north of the Antarctic Circle. Okay, so they list their cities from north to south. The auto grading is assuming north to south. If they don't do north to south, the auto grading will destroy them. And so, there's a message here, but you may want to reinforce it. They put their latitudes here that they're going to measure from Stellarium, the length of day that they measure from Stellarium for their 5 cities for all 4 seasons. So they're doing a lot of measurements. Again, that's the idea, to develop an intuition. As they're doing them, just out of boredom, they'll start making predictions. Now, the really smart ones will know it's always 12 hours on the equinox, no matter where you are on the globe. But we tell them that they should go in and make their own measurements. Don't assume you know the answer, because it's actually not 12, because atmospheric refraction pushes the sun up. So the length of day is actually more than 12 hours. In fact, a little fun tidbit, you can ask the question, can you ever have a total solar eclipse when both the sun and the moon are up? When you teach eclipses, it's always, moon, sun, earth, in that order. But if it happens right when the sun is setting or rising and the moon is setting or rising, the atmospheric refraction will push them both up. And so you will see, you can have a total eclipse with the moon in the sky. Anyway, just a little fun tidbit. So it's actually more like 12.3. We encourage them to measure and confirm their hypothesis instead of just use their hypothesis to get out of making measurements. And sign their name, and then they're going to graph it. And I may go over a few minutes today, but if you have to go, just catch the final few minutes by video. So they graph it. There's a tutorial on how to do that. And that link will take them to our new graphing site. Here it is. and they'll be confronted with this screen. They can either use the old tool, and the videos use the old tool right now, or the new tool. We're going to retire the old tool. The new tool is better. Oops. And it has currently has all the OPIS graphing utilities. And they're going to be using this first one called Curve. I'll show it to you on the new tool. And for example, in this part of the lab, they're going to be plotting length of day versus latitude for all 4 seasons. So I changed it to 4 curves, and you can add data to it and edit data. You get the idea there. Edit labels. So maybe this is something like length of day versus latitude. The x-axis, we're going to have latitude measured in degrees. Y-axis, length of day measured in hours. And they can label their axes here. Summer solstice. Maybe the first curve, summer solstice. The next one's winter solstice. You can have spaces, but it doesn't give you much time to type them. My programmer is going to fix that. In fact, in the lab, we tell them to be specific. Say northern hemisphere summer solstice, northern hemisphere winter solstice, et cetera, et cetera. And see, then it updates all the axes. It's an important thing for students to learn how to label axes and include units and label titles. Label the key here. You'd finish the key. I didn't. And then when they have it all done, they save the graph. They type their name. That's being imprinted in the EXIF data, and we talked about that before. So you can make sure they made it themselves and they're not submitting one that their friend did. And it will then download and they can upload it into WebAssign. Once they do, it will look like something like this. Actually more precise than this. These measurements were made on the Globe Lab where there's less precision. But you can see here for northern hemisphere summer solstice, the farther north you go, the longer the day is. The opposite for northern hemisphere winter solstice, and the 2 equinoxes hover around 12 hours. And then they discuss it in words. I think that's important. They can make the graph, but having to explain it is where hopefully the connections are made. But this is also what makes grading this lab difficult. As you can imagine, they will butcher these explanations, and it could be mind-numbing to read through over and over and over again. But this is part of the manual grading there. Okay, that is length of day. The second part is directness of illumination. We have this graph here, but it's not made very well. So I always bring a flashlight with me and just do the simple thing. Suppose this is the ground, and here's the sun overhead. So here it's way over, high up in the sky at midday. So direct illumination, same energy over a small area. I'm sure you do this in your regular lectures. And here's a glancing blow. So it's low in the sky. So the same energy spread over a larger area, so less energy per unit area. So clearly length of day matters. The longer the day, the more heating, but also directness of illumination is, of course, a huge effect. They don't necessarily think that until they see this example. They can say, oh yeah, far less light per square centimeter there. Okay. And so then they're going to do the same thing. They're going to practice on Chapel Hill and then do a handful. So let me show you Chapel Hill. Going back to Stellarium here. Let me reset the location to Chapel Hill. And we're still on summer solstice sunrise. So that's good. And I'm going to zoom out. And I put south at the bottom here. Let's bring the date time window back up. And I'm going to change the time. Oops, I'll go by hour until it's pretty much over the southern horizon. But what they really want to do, let's see, I've lost the sun here. Okay, is read, and it's hard to see. There's a little eyeball here, night vision mode, that makes it easier to read the text. They want to find this thing altitude, and they're going to tweak the time. I got my finger on it here until the altitude's as high as it's going to get, somewhere around there. So this is the time when it's midday. The sun is on the meridian. It's as high as it's going to get. And they want the altitude there. It's 78 degrees if I round it off. And so this figure tells them where all the stuff is. They put it here. In the globe version, they calculate a percent error. This is something new that we've added, a lot of vocabulary. When I made this lab, I made a conscious decision to use as little vocabulary as possible. Though often when you teach this in lecture, there's all sorts of vocabulary. What's the difference between longitude, latitude, right ascension, declination, azimuth, altitude, the difference between pole, celestial pole, zenith, difference between celestial equator, meridian, ecliptic. And so we've created a supplementary guide here that walks through all these things. I won't go through it due to lack of time, but all the terms are defined and shown in different coordinate systems and the basic effects. So that's there. The lab, though, is consciously written to use the bare minimum amount of terminology so it's accessible to as many people as possible. Okay. Then it's going to be the repetition part. They're going to pick 4 sites, all northern hemisphere. One is the North Pole. We picked that for them. And then something a few degrees south of the Arctic Circle, something between the Arctic and Tropic of Cancer, and something a few degrees north of the Tropic of Cancer. And they can reuse Chapel Hill, for example. For the North Pole, they can't look it up, but they just type in latitude 90, and that puts Stellarium at the North Pole. And then it's the same deal. North Pole, and then the 3 cities from north to south, the latitudes, and the angle above the horizon at midday for the sun. And the only one they can't do is winter solstice at the North Pole, because the highest the sun gets is 23 degrees below the horizon, so we give them that one. And they sign their name, go to the graphing website, make their graph, and it should look something like this. The higher up you go, the lower the sun is in the sky at midday, though it's higher in summer, lower in winter, and both in the middle in the equinox. Again, they're going to try to describe it in words, and you manually grade that. And then we ask them, how do these results differ if we did a southern hemisphere location? They basically run in the opposite direction. Last bit. I'm 2 minutes over, so I'll try to go real quick here. This is measuring the diameter of Earth. The idea is they're going to do a road trip from Winnetoba, Canada to Omaha, Nebraska. It's a nice, long, straight north-south shot of road. So they measure the distance on their trip odometer. And here's a geometry that they're going to see over and over and over again in these labs, where in this case, we have, they're traveling a distance on the Earth that corresponds to a difference in latitude. But the same geometry works with parallax. It works with measuring physical sizes from angular sizes. And so basically it's ratio. This angle divided by the full 360 is this distance divided by the circumference, in this case of the planet. So here's the ratio. Here it is solved for circumference. Distance they look up on Google Maps. We don't make them actually go do that road trip. And then the angular separation, that's the difference in latitude. You get that by measuring how high the sun is at midday at those 2 cities. The difference of that is the difference in latitude. And so they make 2 more measurements. They could do it during any season they want. The distance goes here. The height of the sun at midday at the 2 places go here. You get the difference. They calculate Earth's circumference, show their work, and then divide by pi to get the diameter. Here's the best value. Calculate percent error, discuss sources of error. In the Stellarium version, the only source of error really is Google Maps will overestimate the distance because the road's not perfectly straight. Google Maps has an option where you can have as the crow flies, but I prefer them to do the driven distance and discuss the source of error. And this again is an example of inaccuracy. Everyone will be wrong in the same direction. And then finally, we have a summary exercise where suppose they have a shadow casting stick, a gnomon, or is it gnomon? I don't know if the G is silent. An angle measuring device such as a protractor, coarse tripodometer. How do they do this? It's an opportunity to summarize the whole thing they just did, but we ask them, how do you know when it's midday? And so that's when the stick casts the shortest shadow. They'd use the protractor to get the angle, drive to the other city, repeat, and then do the calculation. So sorry for going 5 minutes over and for kind of speeding at the end there, but I'll shut up, and if you have any questions, go for it.
Question
go ahead.
about the having the days longer and shorter in one hemisphere over the year, and that is said that orientation, and but the latitude and longitudes are we have defined, and then the angle is that we have said that, but how that fits if we do not have anything, but we do not have that latitude and longitude defined the circle in terms of that. Still, yeah, how to explain that?
So in this you mean in this last exercise, how they're doing
Yes.
this without knowing the latitude and longitude?
Okay, yes.
Yep. And so all that matters for this exercise is the difference. And so, so you suppose this is like ancient days and you don't actually have a measurement of the latitude. All they have to do is measure the height of the sun at midday, and that's a particular angle. It would be lower for the higher latitude one and higher for the lower latitude one. The difference in that angle is the difference in latitude. So they don't know the latitudes absolutely, but they can get that difference.
By measuring the stick's shadow at 2 different locations, right?
Yep.
Okay.
Yep.
Got it.
Now they'll just do it in Stellarium, which gives them the latitude, but here they don't actually need to use it. They're going to use the difference in the sun horizon measurement. Brett, you had a question?
Yeah, I was curious about with the auto grader, which mistakes they can make that would get by it. Like, is there an absolute, like if they get absolute numbers wrong, but relative numbers right, does it get marked correct?
Down in this part here?
I think in the earlier parts where they're
Yeah, so in the earlier parts, let's do length of day, for example.
Yeah.
Here we go. It actually doesn't grade anything in the sunrise or sunset columns because we don't know what cities they're going to pick.
Right.
But it will grade length of day. And we know the ranges that are acceptable. We have very generous ranges here.
Okay.
And well, we know the ranges of latitude. So we know the range that the length of day can vary over. And then there's some generous uncertainty as well added in.
Okay.
Yep. Yeah, the auto grader is pretty generous for these kinds of, particularly you're doing the Stellarium version where they're going to have pretty close to exact values. The auto grading was set up for the globe version, which is more inaccurate. So I don't think you need to worry about that.
I have a question.
Yeah.
How long does it take for the students to finish this lab?
This lab, if you do the Stellarium version, it's one meeting. Like we meet for an hour and 50 minutes, and they get it done or mostly done. They can finish up the repetitive parts on their own afterwards if they need to. But most people get it done. If you're doing it on the globe, the measurement process is slower. And so we do it over like 1.5 weeks. In that second half week, we're going to use, now some people get even with the globe, some people get the whole thing done in one session. Some people need to use the entire second session. but we're going to also do our color picture during that second week.
I have access to the 2G for lab 2. Is that information there, is that good enough to set it up for demonstration purpose?
You should have access to 2G and 2S. Now, you may, in the settings in WebAssign, let me go there and show you how to do this. So, now this is your, oh no, oh, that's right, you have access to 2G because you're on mine. You can't see 2S because I don't have 2S on mine. Let's see, if we click reschedule assignments, let's see if this does it here. So I've turned off 2S because I don't want my students to be confused. But you could go through the 2G and get the same thing, or I can add you to someone else's section. Let's just do that. Do that right now. Come on, WebAssign. Let's see. We'll add you to maybe someone who's here. Maybe Jim.
What question you have?
We're gonna add Anna here to one of your sections so she can see the 2S. You use 2S, right?
Yeah. Yeah,
Okay.
that section there I'm not even using. I opened another section I got to give you access to. They haven't yet. So you can use that one as an example.
Okay.
Like I have a, I do the
Yeah,
direct
that's
link.
right. Yeah.
And so I just got to get you added, and they were supposed to add you and they haven't.
So we just got this sorted out. I think your username is this. And what's the institution?
It's a Montclair. You're missing a Q at the end for the username. Yep, there we go.
Oops. Okay. Yep.
Montclair, M-O-N-T. Montclair. Yeah, you have a P there. Yep.
Oh, my typing is terrible.
Montclair, New Jersey?
Yes.
Oh, I grew up right by there.
All right.
Okay. So now you're in this section as well, and you can see the 2S there.
Thank you.
I have a quick question, then. So we have we will resolve with Judy and Brit, but I have in our WebAssign, the access is paid by, it is a paid. Okay, so we have the access codes for
Yeah.
each student. So I have corresponded with you about that, but now it is a paid. So in that case, what should be done to have them access?
They'll have two access codes. One is the class key, which is what I gave you, and that associates them with the class. But then they have to pay, and at UNC Asheville, the university is paying, which is nice. And so that comes with a different code. And so you'll be handing out those different codes. And once they pass 2 weeks from the date I set up the course for you, the start date of the course, they'll be cut off until they enter that access code. But once they enter the code, they're back and nothing was lost.
My student tried that. I have already sent the second code that you said. We paid, UNCA paid, and we got the code.
Okay.
I sent that code corresponding to the student, and she said to me that I will invite her today afternoon so that we can solve that together. But she said that the picture, I guess I sent to you, where it shows that your name and then the course 112, astronomy 112, and then it is expired, it shows. So what she may have been missed? I gave her course code, which is in my WebAssign. Okay,
Mhm.
my WebAssign, there is a course code, course key, and I can click that. It says copied, but that copy has a somehow paste is generates a very long thing. But I just deleted so that there is a UNC and that number for, I guess that is a 4-digit number after that. And yeah.
Yeah, I'm not exactly sure how it works with the code, but did it work for the other students, first of all?
No, I am doing that first time. So and
Okay.
I got the response from her, and I was trying to resolve that. And then I talked with Judy also, and in our so she has said that these codes are paid for UNCA. I was not aware, by the way. That's why I sent that to you. But I knew that WebAssign needs to be paid.
Yeah.
Skynet doesn't need to be paid. That's why, yeah, that I knew. Okay. So you are saying that what
No,
other
it doesn't need to be
students
paid,
has a
but
response?
we get our pay from WebAssign. So,
Yes.
but yeah,
What
if
other?
there's a problem,
Yeah.
First check with your colleagues. After that, it'd be your WebAssign rep. And
Yeah.
if your WebAssign rep is not, because you have a special deal where the universities bought the codes, so I'd check with your rep there. And if you're having problems, I can give you my rep, Bridget Hales, and she's quite helpful.
Okay. Thank you.
Yeah.
Okay.
Yeah, I'm afraid I don't know the answer.
Mm.
Usually these things are student error. Once the student comes in, you sit down and do it with them, then it's
That's
okay.
what I have done for today before the class, so that I know from the student side, from my side, I know, but from the student side, I don't know. That's why I'm planning to invite her to me, and we will solve that together. And then what happens there, and based on then you have shown some other options. Appreciate
right. But if you keep running into a problem, particularly if it's large scale affecting all your students, let me know and I'll get Bridget involved.
Okay, thank you.
Again,
So
I have a
to go. My
question.
class is at next 30 minutes, even not 30 minutes. Appreciate it for all.
Sure.
So is the 2G, is that good to set up the information that I have on WebAssign? Is that enough for me to set that up? Because I see that there's an equipment list or
send me an email and I'll get you, we have a parts list somewhere, and get in my inbox and I'll find that link.
Okay.
In the WebAssign under equipment, there is a list.
Yeah.
But I can send you a parts list with Amazon links.
Okay. All right. Thanks.
So, Dan, I have a question. I mean, maybe said something. I was in a department meeting all this morning, but maybe I already said something. But last night, everything coming back from USAC was blank. Is there an issue?
So that telescope's usually pretty reliable because Daryl Jansen runs it.
Right.
Though it is a roll top enclosure. So there's the possibility that the roll top was closed, yet it was permitting observations. That's unlikely. I thought that was, but Daryl, so send Daryl an email and ask him.
Okay.
Yeah.
It was coming back just totally, and it wasn't like, it was like almost perfectly blank. It was like no flaws or anything. Just everything was put back perfectly.
So it's not like you're shooting clouds and you're seeing out of focus.
No, it was just black, solid black, everything.
So maybe the roll top was closed.
Okay.
Of course, the days are very long up there, but it's getting better, right, as we approach the equinox.
Okay. And then, so I know we have a new moon, and we want to take pictures, in a couple days when we see the crescent. I don't know why I keep forgetting to do things. I haven't done something for a while. I forget, but for some reason I couldn't get it to take a future picture. It just wouldn't let me get to the filter stage or anything.
Oh, so if something's not observable, it doesn't let you observe, except with the moon.
Right. So I was doing the moon and I was trying to get it. And so I was going to try to take a picture in a couple days, but set it up now and I couldn't get it. And I was I can't remember what it was that I have to do that.
Yeah, I have an idea. Add new observation. You do the moon. I swear I'm going to the doctor this afternoon. So, where is the moon? Just out of curiosity. Really close to the sun. Okay,
Right.
good. That's the case we want.
Yep.
I
put that to 0.
Yeah, you definitely need to do that. Okay. And let's see if we can get it to take. Choose filters. Now, so
That's what I was getting, and I was
Yep.
trying to figure out how do I set it up for the future here.
if you would be so kind, send me an email describing, well, I can just do it right now. This is a bug that's not supposed to be there.
Okay.
So here, I'll send a email to Reed right now.
All right, thanks.
Sure.
All right, I'll email Daryl
Okay.
on that.
Any other questions? If not, I'll stop the recording and I'll type this email.
Not a question, just a quick comment, Dan, regarding my question. By the way, thanks for all your help. As far as moving students around in WebAssign, I do have the instructions on how to do that if you want to see them for future reference. So,
Okay. Yeah, if you have multiple sections and they were created under the same course as multiple sections, you can move from one section to another. What's challenging is if there are separate courses, moving from one to another.
there's ways to do the way. I've got some instructions. So from the WebAssign folks, man, I hope you feel better. Geez.
Yeah, I know. Yeah, if you have them written down, send them to me because
Yeah, I'll give you what they sent me. So from all the Cengage people sent me. So just so you have them for future reference.
Thank you. I appreciate it.
No problem.
All right, yeah, if there's nothing else, I'll meet with my TAs. But if there's anything else, speak now or no. We got 2-3 waves. Okay, I'll see y'all.
Thank you, Dan. Bye-bye.